welcome to this problem walkthrough. Today, we'll be tackling LeetCode number 1918, titled KTH Smallest Subarray Sum. This problem challenges us to compute the KTH smallest sum of all possible subarrays efficiently. Stick around as we explore the problem, break it down into digestible steps, and discuss the best approaches to solve it. In this problem, you're tasked with finding the KTH smallest subarray sum from a given integer array nums. A subarray is simply a contiguous sequence of elements within the array, and its sum is the total of all elements in that subarray. For example, if the array is 2, 1, 3, sum of its subarrays would be 2, 2, 1, or 1, 3. The goal is to calculate all possible subarray sums, sort them in ascending order, and return the KTH smallest one. The input includes the array nums, which has a length between 1 and 1000, where each element is between 1 and 100. Additionally, you're given a number k, which represents the rank of the smallest subarray sum you need to find. The output will be a single integer representing this KTH smallest sum. Let's look at some examples to clarify the task further. Consider the first example where nums equals 2, 1, 3, and k equals 4. The output in this case is 3. To understand why, we calculate all possible subarray sums. These are 1, 2, 2, 3, 3, 6, when sorted in ascending order. The fourth smallest value in this sorted list is 3, which becomes our answer. Now, looking at another example, take nums equals 3, 3, 5, 5, with k equals 7. Here, the output is 10. To see why the answer is 10 for the second example, we calculate and sort all subarray sums of the array 3, 3, 5, 5. The sorted sums are 3, 3, 5, 5, 6, 8, 8, 10, 10, 16. The seventh smallest value in this list is 10, so that's the result. Finally, consider a third example where nums equals 1, 2, 3, 4, and k equals 10. For this case, the output is also 10. Looking at the sorted subarray sums, we get 1, 2, 3, 3, 4, 4, 5, 6, 6, 7, 10. The 10th smallest value is 10, which is the answer. These examples highlight the process of calculating, sorting, and selecting the KTH smallest subarray sum. Now, let's discuss the constraints and edge cases for this problem. The length of the array nums is between 1 and 1000, and each element is between 1 and 100. The value of k is always valid, as it lies between 1 and the total number of subarrays, which is n plus 1/2. For edge cases, consider the smallest input size. If nums contains only one element, the output is always that single element, regardless of k. For arrays with large values, such as 100, 100, 100, the algorithm must handle higher subarray sums efficiently. Additionally, arrays with duplicate subarray sums, like 1, 2, 2, must be processed correctly to handle ties. Finally, for maximum input size, where len nums equals 1000, the algorithm must efficiently handle a very large number of subarrays without running into performance issues. These considerations are crucial for solving the problem correctly and efficiently. To tackle this problem, one straightforward approach is the brute force method. Here, we generate all possible subarrays of the input array nums, calculate the sum for each subarray, and store these sums in a list. Once we have all the sums, we can sort the list and directly access the KTH smallest sum. While this method is intuitive and ensures correctness, it is computationally expensive. Generating all subarrays takes n squared time, and calculating their sums adds another layer of complexity. Sorting the resulting list of sums, which contains roughly n plus 1/2 elements, increases the overall complexity to n cubed plus n squared log n squared. This makes the brute force method impractical for large input sizes, as the computation quickly becomes infeasible. Therefore, while simple, this approach doesn't scale well and would fail to meet the performance requirements for larger datasets. A more efficient solution lies in utilizing a binary search approach combined with a sliding window technique. The key insight here is to reframe the problem. Instead of explicitly generating all subarrays and their sums, we focus on finding the smallest sum x such that there are at least k subarrays with sums less than or equal to x. To do this, we perform binary search over the range of possible subarray sums, which spans from the smallest element in nums to the total sum of all elements in nums. For a given midpoint x during the binary search, we count the number of subarrays with sums less than or equal to x. This counting can be efficiently achieved using a sliding window technique, which avoids the need to explicitly list out all subarrays. Depending on this count, we adjust the binary search bounds, narrowing the range until we converge on the desired value. This approach dramatically reduces the computational complexity, with binary search taking O, log, S, where S is the range of possible sums, and the sliding window counting process running in O, N. As a result, the overall complexity is O, N asterisk log, S, which is far more efficient than the brute force method. Several alternative methods were also considered, but they were ultimately not chosen for this problem. For example, a heap-based solution involves maintaining a min-heap to track the smallest subarray sums. While this approach can work, it becomes cumbersome when handling duplicates or certain edge cases, and its complexity is generally less favorable compared to the binary search strategy. Another alternative involved utilizing prefix sum-based optimizations. While prefix sums can accelerate certain computations, they don't directly address the challenge of efficiently finding the kth smallest sum without generating all subarrays. After evaluating these options, the optimized binary search approach was chosen due to its balance of efficiency and clarity. By leveraging binary search to systematically narrow the range of possible sums and combining it with a sliding window to count subarrays, this method achieves a feasible time complexity of O, N asterisk log, S. It avoids the brute force approach's scalability issues while maintaining a structured and elegant solution. The trade-offs are clear: while the brute force method is easier to implement, it is computationally prohibitive. The binary search approach introduces some implementation complexity but offers significant performance benefits, making it the most suitable solution. The pivotal realization that made this solution possible was recognizing that we could use binary search directly on the range of subarray sums while efficiently counting subarrays using a sliding window technique. This insight allowed us to bypass the need for generating all subarrays and solving the problem within reasonable time limits. By reframing the problem and combining these techniques, we were able to deliver a solution that is both computationally efficient and robust, even for large input sizes. This aha moment was crucial for achieving the desired balance between performance and clarity in the approach. In this problem, we are tasked with finding the kth smallest subarray sum from a given array called nums. A subarray is simply a contiguous portion of the array, which means all the elements in the subarray must appear in their original order without skipping any indices. The brute force approach to solve this problem involves generating all possible subarrays of nums, calculating the sum of elements in each subarray, and then sorting these sums. Once we have the sorted list of sums, we can directly access the kth smallest sum. While this method is intuitive and straightforward, it is computationally expensive because the number of subarrays grows rapidly as the size of the array increases. This makes it impractical for larger input sizes, and hence we need to explore more efficient solutions later on. To break down the brute force approach, the first step is to generate all possible subarrays. This can be done using two nested loops. The outer loop iterates over all potential starting indices of the subarray, denoted as I, while the inner loop iterates over all potential ending indices, denoted as j, such that j is always greater than or equal to I. For each pair of indices I and j, we collect the subarray nums, ij plus 1, which includes all elements between these indices. This works because every contiguous subarray is uniquely defined by its starting and ending indices. Once we have the subarrays, the next step is to compute their sums. Instead of storing the subarray itself, we calculate its sum directly and store just the sum. This saves memory, as we avoid storing the actual elements. However, calculating the sum for each subarray repeatedly can be slow, and we will discuss how to optimize this using a prefix sum array later. After generating all the subarray sums, the next step is to sort these sums in ascending order. Sorting ensures that the sums are arranged from the smallest to the largest, allowing us to easily access the kth smallest sum. Once the list is sorted, the kth smallest sum is simply the value at index k1, since arrays in programming are zero-indexed. This approach works because sorting guarantees that the order of the sums is preserved, and we can directly retrieve the kth value without any additional computation. However, sorting the sums adds another layer of computational expense, especially when dealing with a large number of subarrays. This is another area where optimizations can significantly improve the efficiency of the algorithm. One important insight to consider is the sheer number of subarrays generated. For an array of length n, the total number of subarrays is given by the formula n times n plus 1 divided by 2. This quadratic growth means that the number of subarrays increases very quickly as the size of the array increases. Consequently, the time complexity of generating all subarrays is O, n squared. Calculating the sum for each subarray can take additional time, leading to a worst-case complexity of O, n cubed, if each sum is computed from scratch. Sorting the sums introduces an additional cost of O, m log m, where m is the total number of subarrays. When combined, the overall time complexity of the brute force approach is O, n cubed. In terms of space complexity, storing all subarray sums requires O, m, space. This computational and memory overhead makes the brute force approach infeasible for larger arrays, highlighting the need for optimization. To address the inefficiencies of the brute force method, we can introduce several optimizations. The first optimization involves using a prefix sum array. A prefix sum array allows us to compute the sum of any subarray in constant time. Specifically, for a subarray nums, I, j, the sum can be calculated as prefix j plus 1 minus prefix I. This eliminates the need to repeatedly sum elements from scratch, reducing the time complexity of sum calculation to O(1) per subarray. As a result, the overall time complexity improves to O, n squared log n. Another powerful optimization is to avoid sorting altogether by using a heap-based approach. A min heap or max heap can be used to dynamically maintain the k smallest sums as we compute them. This approach further reduces the overhead of sorting and makes the algorithm more efficient for larger inputs. Several data structures play a key role in implementing both the brute force and optimized approaches. The input array nums is the starting point, and its elements are used to generate subarray sums. A prefix sum array, which is optional but highly recommended for optimization, speeds up the calculation of subarray sums by allowing constant time lookups. For further optimizations, a heap data structure, such as a min heap or max heap, is essential. The heap dynamically manages the k smallest sums as they are computed, eliminating the need for a complete sort. Together, these data structures enable us to improve the efficiency of the algorithm while maintaining its correctness. To solve the problem of finding the kth smallest subarray sum, we first define a helper function called count_subarrays. This function calculates how many subarrays have a sum less than or equal to a given value, max_sum. Inside this function, we use a two-pointer approach. We maintain a running sum, cur_sum, and iterate through the array using the end pointer. If the running sum exceeds max_sum, we adjust the start pointer to shrink the window from the left and reduce the sum. Once the window satisfies the condition, we count all valid subarrays ending at the end index by adding end start plus 1 to the total count. This method ensures efficient computation of subarray counts within the given constraint. Next, we move to the main function, kth smallest subarray sum, where we use binary search to find the desired subarray sum. We initialize the search space with left as the smallest element in the array and right as the total sum of all elements. The binary search will help us narrow down the range to the kth smallest subarray sum. In the binary search loop, we calculate the middle value, mid, as the average of left and right. We then determine how many subarrays have a sum less than or equal to mid by calling the count_subarrays function. If the count is less than k, it means the kth smallest subarray sum must be greater than mid, so we adjust the search space by setting left to mid plus 1. Otherwise, we move right to mid to continue narrowing the range. Once the binary search converges, the left pointer will point to the kth smallest subarray sum, which we return as the result. This approach efficiently combines the sliding window technique with binary search to solve the problem within the constraints. Here, we define the helper method countSubarrays that calculates the number of subarrays with a sum less than or equal to a given max sum. This method uses a sliding window approach. We maintain a running sum, cur_sum, which represents the sum of the current window. As we iterate through the array using the end pointer, we add the current element to cur_sum. If the sum exceeds max sum, we shrink the window from the left by moving the start pointer forward and subtracting the corresponding value from cur_sum. Once the window is valid, we calculate the number of subarrays ending at the current end index by adding end start plus 1 to our count. This ensures we account for all valid subarrays within the window. Finally, we return the total count. After defining this helper method, we begin implementing the main method kth_smallest_subarray_sum, where we initialize two variables, left and right. Left is set to the smallest possible subarray sum, and right is set to the largest possible subarray sum. To determine the initial range for binary search, we iterate through the array. For each element, we update left to the smallest number in the array, and right to the sum of all elements in the array, representing the largest subarray sum. Now, we perform a binary search to find the kth_smallest_subarray sum. In each iteration, we calculate the middle value, mid, as the average of left and right. We then use the countSubarrays method to determine how many subarrays have a sum less than or equal to mid. If this count is less than k, it means the kth_smallest sum must be greater, so we move our search space to the right by setting left equals mid plus 1. Otherwise, we narrow the search space by setting right equals mid, indicating that the kth_smallest sum could still be within this range. Once the binary search is complete, left will hold the value of the kth_smallest_subarray sum, which we return as the result. To solve the problem, we start with the first example where nums is 1, 2, 3, and k is 4. The goal is to find the fourth smallest subarray sum. We begin by initializing the bounds for binary search. The left bound is set to the smallest number in the array, which is 1, and the right bound is the total sum of the array, which is 6. Binary search will help us narrow down the range of possible values for the kth smallest subarray sum. For the first iteration, we calculate the midpoint, which is 1 plus 6, divided by 2, giving us 3. Next, we use a helper function, count_subarrays, to determine how many subarrays have a sum less than or equal to 3. Inside count_subarrays, we keep track of the current sum, a starting pointer for the subarray, and a total count of valid subarrays. As we iterate through the array, we add elements to the current sum and count the subarrays that meet the condition. When the sum exceeds the maximum allowed, we shrink the subarray by moving the start pointer forward and adjusting the current sum. For this example, the count of subarrays with sums less than or equal to 3 is 4, which we return to the binary search process. Since the count of subarrays with sums less than or equal to 3 is 4, which matches our target k, we update the right bound to the midpoint, which now becomes 3. Next, we proceed with the second iteration of binary search. The new midpoint is calculated as 1 plus 3, divided by 2, which gives us 2. Again, we call count_subarrays, this time with a maximum sum of 2. Within this function, we iterate through the array, adding elements to the current sum and counting valid subarrays. If the current sum exceeds the limit, we adjust by removing elements from the start of the subarray. In this case, we find that only 2 subarrays have sums less than or equal to 2. These subarrays are 1 and 2. The function returns this count of 2 to the binary search process. Since the count of subarrays with sums less than or equal to 2 is less than k, we adjust the left bound to mid plus 1, which now becomes 3. At this point, the binary search terminates because the left and right bounds have converged, both equaling 3. Therefore, the fourth smallest subarray sum is determined to be 3. Moving on to the second example, nums is 2, 4, 6, and k is 5. Here, we initialize the binary search bounds with left set to the smallest element, which is 2, and right set to the total sum of the array, which is 12. In the first iteration, we calculate the midpoint as 2 plus 12, divided by 2, giving us 7. We then call count_subarrays with a maximum sum of 7. Summarizing the execution, the function finds 4 subarrays with sums less than or equal to 7, 2, 4, 2, 4, and 6. Since the count of 4 is less than k, we update the left bound to mid plus 1, which becomes 8. For the second iteration of binary search, we calculate the new midpoint as 8 plus 12, divided by 2, resulting in 10. We call count_subarrays with a maximum sum of 10. Summarizing the execution, the function identifies 5 subarrays with sums less than or equal to 10, 2, 4, 2, 4, 6, and 4, 6. Since the count matches k, we update the right bound to the midpoint, which is now 10. The binary search terminates when the left and right bounds converge at 10. Thus, the fifth smallest subarray sum is determined to be 10. To understand the time complexity, we start by analyzing the count_subarrays function. This function uses a sliding window approach to count subarrays with sums less than or equal to a given max_sum. For each element in the array, we adjust the start pointer to maintain the subarray's sum within the limit. Since the start pointer only moves forward and never backward, and the end pointer iterates through the array once, the combined iterations of both loops are linear. This gives the count_subarrays function a time complexity of O, n, where n is the length of the array. Next, in the kth smallest subarray sum function, we use binary search to narrow down the range of possible subarray sums. The binary search operates over a range defined by the minimum and maximum possible sums, which can span from the smallest element in the array to the total sum of all elements. While this range can grow large, binary search reduces it logarithmically, requiring O, log, sum, nums, iterations. In each iteration, we call the count_subarrays function, which takes O, n, time. Therefore, the overall time complexity of the solution becomes O, n asterisk log, sum, nums. Now, let's discuss the space complexity. In the count_subarrays function, only a few integer variables are used, such as count, cur_sum, start, and end. These variables do not depend on the size of the input array, so the function operates in constant space, or O1. Similarly, the kth smallest subarray sum function, which utilizes binary search, does not require any additional data structures. All computations are done in place, and no extra memory is allocated based on the size of the input. As a result, the space complexity of both count_subarrays and kth smallest subarray sum is O1. Combining these, the overall space complexity of the solution remains O1, making it very memory efficient. To better appreciate the efficiency of our optimized approach, let's compare it to the brute force method. A naive solution would generate all possible subarrays of the array nums, calculate their sums, and then sort these sums to find the kth smallest. Since there are O, n squared, subarrays, generating their sums takes O, n squared, time, and sorting these sums requires O, n squared asterisk log, n squared, time, which simplifies to O, n squared asterisk log, n. This brute force method also requires O, n squared, space to store all subarray sums. In contrast, the optimized solution avoids explicitly generating subarrays and instead uses a combination of binary search and the sliding window technique. This reduces the time complexity to O, n asterisk log, sum, nums, as binary search narrows the range of sums logarithmically, and counting subarrays for each candidate sum takes linear time. Additionally, the space complexity is reduced from O, n squared, to O1, since no extra storage is needed. Clearly, the optimized approach is far more efficient in both time and space, especially for large input arrays. Finally, let's analyze the best, average, and worst cases for the solution. In the best case, binary search converges quickly to the target subarray sum, requiring fewer iterations. However, since the time complexity is dominated by the need to count subarrays in each binary search step, the overall complexity still remains O, n asterisk log, sum, nums. In the worst case, binary search performs the maximum number of iterations, which is proportional to O, log, sum, nums, and each iteration involves counting subarrays in O, n, time. Even in this scenario, the overall complexity does not exceed O, n asterisk log, sum, nums. On average, the binary search converges in O, log, sum, nums, iterations, with each iteration taking O, n, time to count subarrays. Therefore, the average case complexity is the same as the worst case complexity, O, n asterisk log, sum, nums. When solving this problem, there are several common mistakes to be aware of. First, overlooking edge cases can lead to incorrect results or even runtime errors. For example, if the input array is empty or the value of k exceeds the total number of subarrays, your solution should handle these gracefully, perhaps by returning a default value or an error. Additionally, arrays with duplicate elements can complicate the computation if not handled properly. Another frequent issue is relying on an inefficient brute force approach. Generating all possible subarrays and then calculating their sums results in a cubic time complexity, O, n cubed, which becomes infeasible for larger arrays, especially when n is around 10,000. This can cause your solution to time out due to the sheer number of computations. Sorting mistakes are another pitfall to avoid. If you misunderstand the relationship between subarray sums and their indices, you may encounter incorrect results or out-of-bound errors. Always ensure sorting is based on the sum values, not the indices. Finally, it's crucial not to confuse the kth smallest and kth largest elements. Under pressure, it's easy to solve the wrong variation of the problem. Always double-check whether the problem specifies kth smallest or kth largest before starting your implementation. Now, moving on to some additional tips and insights, improper use of priority queues is another common mistake. For the kth smallest element, a max heap of size k is typically the best choice, as it helps maintain constant space while efficiently tracking the kth smallest value. Mismanaging heaps can lead to excessive memory usage or incorrect results. From an interview perspective, efficiency is key. Interviewers are often looking for optimized solutions, so it's important to know alternatives to brute force. For instance, using binary search combined with prefix sums can significantly reduce time complexity. Prefix sums, in particular, are a critical concept to understand because they allow you to compute subarray sums in constant time, reducing the overall complexity of your solution. Additionally, be comfortable explaining and implementing heap-based solutions, as these are frequently used in problems involving kth smallest or largest elements. Being familiar with both min heaps and max heaps, along with their trade-offs in terms of time and space complexity, is essential. Lastly, always clarify the problem's requirements up front. Confirm whether duplicates in the array should be considered and whether the task involves finding the kth smallest or largest element. These details can significantly affect your approach. To deepen your understanding, it's helpful to explore related problems. For instance, LeetCode 215 asks for the kth largest element in an array, while LeetCode 378 involves finding the kth smallest element in a sorted matrix. Problems like LeetCode 560, which focuses on subarray sums equaling a target value, and LeetCode 719, which deals with finding the kth smallest pair distance, are also relevant and can help you practice similar concepts. When it comes to alternative approaches, one powerful method is using prefix sums combined with binary search. This technique allows you to calculate subarray sums in constant time and efficiently narrow down the kth smallest value, reducing the overall complexity to n² sum. However, this method can be challenging to implement correctly. Another option is a heap-based approach, which uses a max heap of size k to track the kth smallest sums during iteration. This method is intuitive and easier to implement but requires additional space. Finally, a divide-and-conquer approach can be used to split the array and combine results efficiently. While this method is well-suited for parallel computation, it can be quite complex to implement in a typical coding interview. Choosing the right approach often depends on the problem constraints and the time you have available to solve it. Great work! We've now completed the walkthrough of LeetCode number 1918, kth smallest subarray sum. We reviewed the problem, explored different approaches, and highlighted the optimal solution. Remember to practice similar problems to reinforce these concepts. Thank you for watching. Be sure to like, comment, and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!